Hello everyone, today we are going to talk about solving exponential equations. So we'll do a number of examples, but an exponential equation is an equation where the unknown, the variable, is in the exponent. And the main way to solve these is by applying logarithms. So what we first want to do is we want to review some of our properties of logarithms that we'll be using. So we kind of had two sets of properties, our general properties of logarithms. So there were three of those. The first says that if we had the log, so I'm just going to write the log. Again, this applies as long as the bases match. So the log of m plus the log of n, that's equal to the log of m times n. And if you do the same thing where the logs match, but instead it's subtraction, so the log of m minus the log of n, this can be simplified to the log of m divided by n. And third, so this is maybe the most important property for solving logarithms, the log of m to the p power. What we can do is we can bring that p out front and make it p times the log of m. Let me mention, we also had inverse properties. So these are very dependent upon which base you're using. So I will include the base here. So the main property we'll be using in this lecture is if you have the log base b of b raised to the x, this is equal to x. The other property is if you have b raised to the log base b of x, this is equal to x, but only for x greater than 0 because of domain restrictions due to the logarithm. So in particular, we also want to recall, so for solving these equations, a lot of calculators only have two logarithms available. So some newer calculators have more options, but we have, if we just write the log of x, this means log base 10 of x, so it will cancel with 10 to a power. And if we write the natural log of x, this is the same as the log base e of x, where e is Euler's number, which is about 2.71828, so on. So an irrational number whose decimal expansion continues ad infinitum. Okay, so let's see. These are the properties that we're going to be making use of to solve the equations. So let's go through just a number of equations to see how these things apply. So the main ones we're going to be using are kind of property 3 right here and property 1 under the inverse property. So let's just note that. Star and double star are the most frequently used properties. When solving exponential equations. So I'm not saying the other properties aren't as useful, I'm just saying they typically occur less frequently with most of the normal examples. Next time we'll talk about logarithmic equations, and in logarithmic equations we will be using that inverse property 2 quite frequently. So just trying to give you a little bit of a heads up for today's lecture, not saying that that is necessarily something that's set in stone. So let's go ahead and look at the first example. So here we go. Basically in all of these examples we're just trying to solve for x. Or whatever letter the problem might indicate. For all of mine, it's going to be x, but in some homework problems, you might see t or something like that. But I'm just going to write solve for x. So the indicator that you want to apply the logarithm at some point is that you see the unknown in the exponent. So that's happening right here. So we see 2 to the x equals 24. So that indicates that we're going to apply the logarithm. Usually what you first want to do is isolate the exponential quantity if there's something in front, but in this case there's nothing there. So as I mentioned, usually we're going to want to get some sort of numerical approximation for these. So that means that we want to use one of the buttons that's on our calculator. So typically that's either common log or natural log. So let's take the common log of both sides. So we have the log of 2 to the x is equal to the log of 24. So we can now use property number 3 to bring that x down in front. And then what you want to do is just divide both sides by the log of 2. X is being multiplied by the log of 2, so we divide by the log of 2 to isolate x. So then we can type that value into our calculator to get an approximation. So let's go ahead and do that now. Let's say the log of 24 divided by the log of 2. So that comes out to about 4.58 if you round to 2 decimal places. Okay, let's try another one. So let me do this one over here to the right. So let's say we have just a little bit, one more step maybe to this problem. 3 to the x minus 1 equals 12. Again, the exponential quantity is not being multiplied or divided by anything. It's just 3 raised to the x minus 1. So we can start just by taking the log of both sides. So we take the log of 3 to the x minus 1 on both sides. So the thing to remember, whenever you bring down the exponent, the entire exponent is being multiplied. So I need to put parentheses around that x minus 1. So I have x minus 1 times the log of 3, and that's going to equal the log of 12. So then what I need to do is I need to distribute. So I have x times the log of 3 minus 1 times the log of 3, which I can just write down as minus log of 3, and that equals the log of 12. So what we want to do is we want to solve first for x log 3. So since you're subtracting log of 3, we want to add log 3 to both sides. So we have x log 3 equals the log of 12 plus the log of 3. Now, typically, I would just leave it alone like that, but you could, if you want to, apply property number 1, and since we have log of 12 plus log of 3, you could actually write the right-hand side as the log of 36. Now, that's not absolutely necessary to get the numerical approximation, but it will make it a little bit easier to type into your calculator. So the last thing to do to solve for x, we want to divide both sides by the log of 3. So we can go ahead and do that right here. And so x is equal to that entire expression, log of 12 plus log of 3 divided by the log of 3. So you want to type that into your calculator. And to get an approximate numerical value, that comes out to about 3.26. If you round to 2 places once again. So that is the second one. So kind of an extra step there because we have to distribute once we bring down the exponent. Okay, so let's look at another example. So let's look at one similar to b, but in this case, it's going to be e to the 3x minus 5 equals 64. Now, whenever you see e, it's going to make more sense to use the natural logarithm. And that's because that inverse property we marked as double star, we're going to be able to use that. So if we take the natural log of both sides here, you get the natural log of e to the 3x minus 5 equals the natural log of 64. So then what happens is that natural log cancels out with the e on the left-hand side, so we just get the exponent, 3x minus 5. And on the right-hand side, we get the natural log of 64. So the natural log of 64 is just a number, so that's what we're left with is really just a linear equation in the variable x. So it's 2 steps to solving it. First, adding 5 to both sides. So we have 3x equals 5 plus the natural log of 64. And then once we've done that, we can divide both sides by 3. So we're left with x is 5 plus the natural log of 64 over 3, which we can do in our calculator. And that should come out to about 3.05. Okay, so another example, D, let's say we have 10 to the 1 minus 2x, and that equals 0.34. Now, in the previous problem, part C, it made sense to use the natural log because it canceled out with a base of e. Well, in this case, we have a base of 10, and the common log will cancel out with that. So we want to take the common log of both sides here. So usually it doesn't matter, but if you see a base of e or a base of 10, one of them is certainly going to be preferable in terms of efficiency. So we have the log of 10 to the 1 minus 2x, and that'll equal the log of 0.34. So then again, we want to bring down the exponent. Actually, we don't need to bring down the exponent because we use the common log, so it just cancels. So we end up with just whatever that exponent was, which was 1 minus 2x, and that'll equal the log of 0.34. Okay, so then what are we doing? Well, we have a positive 1 that we need to subtract, and then we're going to have to divide by a negative 2. So we start by subtracting 1 on each side. So we have minus 2x equals the log of 0.34 minus 1. And then to get x by itself, we just want to divide by negative 2. So x is that quantity log of 0.34 minus 1 divided by negative 2, and that comes out to about 0.73 if you round to 2 spots. Okay, so let's increase the difficulty a little bit. These things can be a little bit messier if so far what we've seen is an exponential quantity on one side and just a regular number on the other side. So what if both sides contain an exponential quantity of some sort? So we can look at such an example. So let's say we have 10 raised to the x plus 5, and that's equal to 7 raised to the 2x minus 1. Now, again, it's still going to make more sense to use the common log because we see a base of 10 somewhere. So we'll take the common log of both sides. So on the right, we get cancellation, which just leaves us with x plus 5. But on the right-hand side, we don't get cancellation because the base is 7 and not 10. So what we have to do is use property number 3, that one that we start at the very top. So we bring down 2x minus 1 in parentheses, and we essentially distribute. So let me do this one in 2 different ways, because a lot of times I'll see students get lost just because there's so much being written down. But because I allow you to use an approximate decimal answer for these problems, we could just plug it into the calculator. So we'll provide an alternative method to the right-hand side once we finish this in the standard way. So the first thing we want to do is we want to distribute the log of 7. So the log of 7 is just a number, so we end up with 2 log of 7 times x minus the log of 7 distributing. Okay, so now we see x's on both sides of the equation. So what we want to do is we want to move the x's to one side of the equation and the regular numbers to the other side. So what I'm going to do is I'm going to move the terms that contain an x to the right and the terms that do not to the left. So basically I can do that by subtracting x and adding the log of 7. So I'll do that to both sides. So on the left-hand side, I'll just be left with my 5 plus the log of 7. And on the right-hand side, I'll have my 2 log 7 times x minus x. So now we see x in 2 spots on the right, but that's okay because we can factor it out. So we'll be left with 5 plus the log of 7, and that'll equal x times 2 log 7 minus 1. And then we can solve for x by dividing by that parenthetical quantity. So on both sides, we'll have 2 log of 7 minus 1. So divide by 2 log 7 minus 1. So that's our value for x, technically 5 plus log of 7 divided by 2 log 7 minus 1. So that's the value for x on both sides. Or excuse me, that's the exact value for x, so we can get a decimal approximation by plugging all of that into the calculator, and that comes out to about 8.47. So what is the alternative? The alternative is using decimal approximations earlier. So alternative, and this is technically not as good because you're not going to find the exact answer, but it may help you avoid making some common mistakes. So what we're going to do is we're going to take this step right here and move it over here. And what I'm going to do is I am going to approximate the value of the log of 7. So if I approximate the value of the log of 7, I just type that into my calculator and I get about 0.845. So this is being multiplied by 0.845. So now what I have is I just have an equation where I can multiply on the right-hand side by this 0.845, and I'll be able to combine all my terms just by multiplying and adding with decimals. So I'll have x plus 5 equals, so I multiply 2 by 0.845, and I get 1.69x minus 0.845. So then same deal, we want to move our x's and put those on one side and the regular values on the other side. So I'll do the same. I'll subtract x. But now I'm just adding 0.845 instead of something that looks much more complicated. So subtract x and add 0.845. So on the left, I end up with 5.845. And on the right, I just end up with 0.69x. So that's all I have to do is now divide by 0.69. And you'll get the same decimal approximation as your final answer. We'll end up with x is about 8.47. So a lot of people prefer this alternative method. It does save quite a few steps, but like I said, you're not going to get the exact value. You're only going to get the approximate value. So this alternate method is kind of in place of the standard way, but you don't have to factor or worry about quite as much algebra. So I'm okay if you do it that way, and most of my problems I'll just ask for the final answer and round it to 2 decimal places. Okay, so let's look at a couple others. So still, that's not as difficult as they can get because one of the sides still ended up with some cancellation. So let's do another where nothing cancels. So this one I will just do using the rounding, using the approximate method. If you don't and you want to find the exact value, it does take a lot longer, but I would encourage you to try it if you're really comfortable with the algebra. So this one we want to solve for x, where the left side is 4 raised to the 2x minus 1, and the right is 3 to the 2x minus 3. So again, we want to take log of both sides. It doesn't matter what logarithm we use here, because if we only have log and natural log available, neither one is going to provide us with any cancellation. So let's start by taking the log of both sides. So we have the log of 4 raised to the 2x minus 1 on the left, and we have the log of 3 raised to the 2x minus 3 on the right. So what we want to do is bring down both of those exponents and remember to use parentheses. So we have 2x minus 1 times the log of 4 equals 2x minus 3 times the log of 3. And so then we can, if we're approximating, what we want to do is just plug log of 4 and log of 3 into our calculators. So the log of 4 comes out to 0.602. So on the left we have 2x minus 1 times 0.602. And on the right we have 2x minus 3 times the log of 3, which is 0.477. And again, I'm using 3 decimal places here, just because my final solution I intend to round to 2, so it's going to give me a little additional accuracy. So on the left-hand side, I want to distribute, so I get 1.204x minus 0.602, and that will equal 0.954x minus 1.431. So again, we want to move our x's to one side and our regular values to the other. So I'll move the x's to the left this time and my regular values to the right hand side. So I want to subtract 0.954x and add 0.602. So we end up with 0.25x on the left, and on the right we have negative 0.829. So now what we want to do is just divide by 0.25 on both sides. So we get our value for x, which is approximately negative 0.3316. If you were rounding to 2 places, you could round that to negative 3.32. But that is it for this example. Okay, so let me look at maybe 2 more where we can apply properties 1 and 2 that we haven't seen so far. So yeah, let me show you an example where at some point we would have to use property number 1. So let's say we have I don't know, maybe 5 times 2 to the x equals 8 times 7 to the let's just say x. Okay, so we want to know when are these quantities the same. Now the problem is we're multiplying both of our exponential quantities by some number. So we're not going to be able to get rid of that. So taking a logarithm is not something that's going to work because we can't bring down the exponent right away. So really what we're going to want to do is use property number 1 here. So let's suppose we take the log of both sides. Let's say we have the log of 5 times 2 to the x, and that'll equal the log of 8 times 7 to the x. Now the problem here is that we cannot simply bring the x out in front because on the left we're multiplying it by 5 and on the right we're multiplying it by 8. So what we can do is we can use property number 1 to write this as the log of 5 plus the log of 2 to the x. And on the right hand side we can write the log of 8 plus the log of 7 to the x. So now we can bring the x's down in the second term on the left and the second term on the right. So I have the log of 5 plus x times the log of 2, and that'll equal the log of 8 plus x times the log of 7. So we had to use property number 1 before we could use property number 3. So now again we can just use some approximations if we're only after 2 decimal places. So let's go ahead and do that. So we have 0.699. And again, I'm just plugging these into the calculator. Plus 0.301x. And that'll equal 0.903. Plus 0.845x. And then we just have a linear equation in x that we want to solve. So let's go ahead and move the regular numbers to the left. So we'll be subtracting 0.903 and the x's to the right. So subtracting 0.301x. So what are we left with? We're left with 0.544x, and that's equal to negative 0.204. And then we want to divide both sides by 0.544. So we have our approximate value for x. So it comes out to 0.375. So if we want to do one last example, maybe we will involve some division, so we have to use property 4. So let's say we have, I don't know, let's say 3 to the 2x. A bit messy. So 3 to the 2x divided by 14, and let's say this equals 2 times 6x. Okay, so same kind of story goes here as in the previous problem. We want to take log of both sides, but we cannot use the exponent property right away because we have some other values involved, some coefficients multiplying and divided by each exponential quantity. So on the left-hand side, that can become subtraction. So the log of 3 to the 2x minus the log of 14. And on the right-hand side, we use property number 1, so it becomes addition. Log of 2 plus log of 6 to the x. And then we can bring down the exponents. So we'll have 2x log of 3 minus the log of 14. And that'll equal the log of 2 plus x log of 6. And then we can go to our calculator. So first we want to put in 2 times the log of 3. So that comes out to 0.954x minus the log of 14, which is 1.146. And then we have the log of 2, which is 0.301, plus the log of 6 times x, so 0.778x. Then we just have a linear equation in x again. So let's go ahead and move the x's to the left. So we want to subtract 0.7 1.178x, and then we want to move the regular numbers to the right, so we'll add 1.146 and do the same on the right hand side. So 1.146 plus, actually we're subtracting the 0.778. So what do we end up with? We end up with 0.176x on the left, and on the right we end up with 1.447. So then we want to divide by 0.176 on both sides. So we end up with x is about 8.22 if we round 2 spots. Okay, so that's it for exponential equations. Next time we will talk about logarithmic equations, and the only difference there is instead of taking logs, we'll be exponentiating and using the other inverse property to eliminate the logarithms. So this is Dr. Lennon signing off.